Assalamu alaikum. How are you, my dear students? Hope you'll be fine and okay. Today is our lecture number 8, Unit 11, Electrostatics. Today's topics are electric potential energy, and electric potential due to a point. So this is what we will learn in our today lecture, and the electric potential energy and electric potential due to a point charge is an extremely important topic as per your exam is concerned. Electric potential is very easy because you have learned some part of the electric potential in the previous class also. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. So the first is electric potential. That what is electric potential? Electric potential is, in fact, it is the amount of energy supplied to a charge while moving it from while while moving it from one point into another point against the electric field that is known as the electric potential. So electric potential is what? Electric potential is, in fact, the work done. It is what? The work done while moving moving a positive charge from one point to another point against the electric field against the electric field the electric field or it is the electric potential is in, we can also say that electric potential is in fact the change in potential energy of a charge that is of a positive test charge q naught while moving it from one point into another point against the electric field. So electric potential is in fact what? The change in potential energy of the charge while moving it between any 2 points against the electric field. So in order to explain the phenomena of the electric potential, class, there is potential difference also, and I will come to the potential difference inshallah once I just finish this potential difference. There is difference between electric potential and a potential difference. So we'll visit this a bit later once I explain this to you. So now you see, we have two plates, one the plate A which is positively charged and the other plate B which is negatively charged. Usually we take the positively charged plate as the positively charged plate is at higher potential and the charge plate, the negatively charged plate is at the lower potential. Now you see that, look, if you have a charge particle and if you release or allow the charge particle to allow it to the inside uniform electric field, as you see this is a uniform electric field because the plates are parallel, and in the Gauss law you know that the parallel plates can produce what? Uniform electric field, and this is one of the reasons that you see that the electric field lines are equally spaced. This is the direction of the electric field intensity from the positively charged plate towards the negatively charged plate. Let we have a charge q, this q naught charge, a positive charge, and let's suppose I want to move this charge from the plate B, right, from here, from this point, and if for example the charge be moved from the point B, from the plate B towards the plate A, right? So if you just see, look, if I release the charge or if I allow the charge to enter into this uniform electric field, then the charge will move from what? The charge will move from the direction, that is from the plate A towards the plate B in the direction of the electric field intensity. Why? Because the like charges repel each other. So that, but we want to move the charge from the point B to the point A without disturbing the equilibrium state of the charge, right? So now what going to happen here? Then if we want to move the charge against the electric field, then from the plate A to the plate B, then definitely, because you know that we want to move this charge from what? From the direction of what? This charge Q naught, that is from the B to A, then definitely we must apply a force, right? Uh, Work must be done. So the work that we do will be what? Will be this work done will between the plate A and B. This work done will be definitely VB to A. Why? Because we want to move the positive charge from the point A towards the point B. So this is what? This is the this may be the force that will be applied on the charged particle, right? And then there is another force, because we are doing work done against the electrostatic force, and that force, right, which push the charge towards the plate B, that force is in this direction. We actually want to raise the charge against this electrostatic force Q naught into E. So definitely work must be done, and this work done will then appear as the potential energy stored in the charge. That is what we can say, that it is definitely it is move against the electric field, so work must be done. So this work will appear as the change in the potential energy of the charge, and this change in potential energy is denoted by delta U, and it will be equal to the work done between the 2 points A and B, right, and the positive charge. So where UA and UB represents the potential energy of the charge at the point A and at the point B, exactly in the same way as if I give you a kind of example. For example, if it is Earth, right, and if you want to move a body from one point to another point inside the earth gravitational field, so if you want to move the body from the point A towards the point B, then look what happens, that since the force is attractive, so you see that you have the potential energy of the body at the point A, and then you have the potential energy of the body at the point B. So what is the change in the potential energy? Definitely, it will be the potential energy from the point B to potential energy at the point A. So it has potential energy this, and it has the potential energy this. So the work done while moving the charge, while moving a mass or a body inside the gravitational field, that work done will be in fact equal to what? It will be equal to the change in potential energy. So exactly in the same manner, the same thing happens here. But what is the problem? The problem here is that at this, we have the potential energy of the charged particle UA there, and here we have at as UB. This is called the electrostatic potential energy. So definitely that, since point A is at higher potential, so the charge will experience more repelling force near the positively charged plate. There will be a greater force on it there. So this will be then written as UA into UB, which will be equal to B into A. The work done while moving the charge from B to A. So now look, what actually we are now going to do this thing, since this is the work done per unit charge, this delta U. So dividing this by Q naught, this delta U, and this work done be A by what? By Q naught, right? By Q naught. So this is in fact what? This electrostatic potential Q naught it is equal to, but we know that this is what, that this is the potential difference, right? This is what, this, as you remember in class 10, that potential difference we have defined, potential difference. What was potential difference? It was the work done per unit charge, per unit charge while moving it against the electric field. While moving it against what? While moving it against the electric field. Work done per unit charge. So you see that, look, you have the electrostatic, that is the, you have the potential at the point V as VB, and here you have the potential at the point A as VA. So this we can write that this electrostatic potential is equal to Q naught into VA minus VB. Why? Because point A is at higher potential, yeah, the plate is at higher, this is at higher potential, then this is at higher potential VA, then the plate B, which is at lower potential, which we set at lower potential. So this is what we can write, that this delta U into Q naught is equal to what? It is equal to delta V, or the electrostatic potential energy, the amount of energy supplied while moving it between any 2 points inside the electric field is equal into delta, it is equal to delta U. It is equal to what? It is equal to delta, it is equal to Q naught into delta U. So you see that this is in fact what? So what we can, in other words, are, we can also write, since yeah, since we know that uh, earlier that delta U is in fact what? It is equal to the work done from B to A. So the work done from B to A is actually equal to what? Q naught into the potential difference between the 2 points. Usually this potential difference is known to us. Now, what is the potential difference? This potential difference, right? In fact, it is what? This potential difference, we can define it in another way, is that it is the amount of what? It is the amount of energy supplied by the charge, supplied by the charge as it moves, as it moves between any 2 points inside the electric field, inside the electric field, right? For the positive charge, in the direction of the electric field, in the for the negative charge, in the direction opposite to the direction of the electric field. While, look, the electric potential is in fact, this electric potential is in fact what? It is the amount of what? It is the amount of energy supplied to the charge. This is what? This is supplied to the charge, the charge, to move it against the electric field. So definitely energy must be, definitely the energy must be from the some external sources, right? Mechanical energy or whatsoever. Here, what is that is, in this situation, in this case, in the case of electric potential, the non-electrical energies are in fact converted to electrical energy. While in this case, this is one of the example of the conversion of what? Of the conversion of electrical energy into non-electrical energy. Electrical energy into what? Into non-electrical energy. Non-electrical. For example, how? Because when you raise the charge from the point B towards the point A. And when you allow the charge to move, definitely the charge will move in the direction of the electric field, a positive test charge Q naught. So it will move in the direction of what? In the direction of the electric field. So definitely it has a kinetic energy associated with it. And we use that kinetic energy to change it into heat energy, to light energy, or to any other form of energies. So that is the difference between electrostatic potential or electric potential and a potential difference. In one, it is in the energy supplied per unit charge, while the other case energy supplied per the energy supplied by the charge, right? So that is the difference between the two. Clear? So that is how this energy, it is measured in joule, right? Or in on a smaller scale, it may be also measured in electron volt. So remember, usually that is on the nuclear scale, or on nuclear scale or small scale. Nuclear or small scale. We use what? We use electron volt. What? Electron volt or EV. Right? This is what? It is not the unit of potential difference. Remember, the unit of potential difference is what? The unit of potential difference is volt. This is what you have learned in class 10. Why? Joules per coulomb. What is the unit of energy? Joule. And what is the unit of charge? Coulomb. So definitely here you have the unit as what? Volt. And 1 volt is equal to what? Joule per coulomb. Here, that is the unit of energy is joule, but on the nuclear scale or on electrical scale, joule is a very large unit. So we use electron volt. So what is the electron volt? It is the unit of energy on a smaller scale. Why? Because this is what? It is the amount of energy. The amount of what? The amount of energy released by what? Released by the electron. Released by the electron as it moves between 2 points, inside the electric field, inside the electric field, having potential difference, having potential difference 1 volt, right? So if the potential difference is 1 volt, then this energy release will be what? This 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, right? That is 1 electron volt. Why? Because if you just see, look, the charge on electron is 1.6. Look, what I'll be, this is so easy. Here, for example, the charge is what? That is one, the charge on 1 electron is how much? If charge is equal to 1 electron, that of 1 electron, if 1 electron moves, so 1.6 into 10 to the power minus 19 coulomb, and we have set the potential difference to 1 volt, and coulomb into volt always give you joule. So 1 electron volt is equal to 1 electron volt equals 1.6 into 10 to the power minus 19 joule. And later on, mostly we will use this, right? So that is all about the electrostatic potential and potential difference. And what is the difference between the two? I explain it to you that electrostatic potential is in fact the energy supplied to move the positive test charge against the electric field, while potential difference is the amount of energy supplied by a unit positive test charge as it moves between any 2 points inside the electric field. And if it is a positive test charge, so the direction must be definitely along the direction of the electric field intensity, right? So both the energies are measured in on a smaller scale as in electron volt, and on SI scale it is measured in volt, the potential difference and the electrostatic potential, right? While electrostatic potential energy and potential difference, they measured in what? In electron volt, right? The next topic is the electrostatic potential due to what? Number two, electrostatic potential due to due to a point charge. Due to what? Due to a point charge. Now we are going to derive the relation for the electrostatic potential to derive the relation for the electrostatic potential due to a point charge. Now, what is electrostatic potential due to a point charge? It is in fact what? In fact, it is the amount of energy, amount of what? It is the amount of energy required by a unit positive charge, by a unit positive charge to move it from infinity, from what? From infinity to any point or that point inside the electric field, inside the electric electric field, right? This electric potential will be given, that is the electrostatic potential, the electrostatic potential energy. This will be given by what? This electric potential is in fact given by the relation. It is given by the relation is oh, I'm so sorry. This is given by this electric potential is in fact given by the relation is V equals, due to point charge, this is equal is K Q by R, or we can write 1 over 4 pi epsilon naught Q by R. Right now, I will derive this later, but first let me explain it to you. This is what? This is the magnitude of the source charge, right? That is a positive charge. The source charge Q is indicated in the diagram there. Is it clear? And here R is the distance, right, at which the charge particle is moved inside the field, electric field. So it is the distance from what? The distance between what? The distance between source and test charge, source and test charge. Now you know that every field surround, that is which surround the charge, then there is a region where all other test charge are not in the influence of that charge, right? So this is for example, look, this is, it is a positive test charge, and definitely this charge has what? The field decreases, the field of the charge decreases. As you know, the electric field intensity A is inversely proportional to 1 over R square. So definitely at a certain distance, right, the field may slowly, that is decreases and may it vanish, right? So we choose a point where there is what? That a point called infinity, where the electrostatic force of attraction or repulsion on the charged particle we consider as zero. So we can move the charge there anywhere without experiencing any force. Why? Because there is no repulsion or attraction on the charge at that infinity point. Now we want to move the charged particle from infinity into the direction of what? Into the direction of the electric field. So here in this equation you see that this electric potential is what? It is inversely proportional to 1 over R. Now we will discuss this, and it is directly proportional to the test charge. So you see, let us derive this equation derivation, that how we can derive derivation. Now let us bring this here. And let me place it here for our clear understanding. Just make it bigger. as you see. Okay, look, first of all, to derive this, we want to move the charge particle. As you see, this, there is a test charge. This test charge is what, this test charge, it may, you may denote it by q or by q naught. I, this is the test charge, right? That is q is the source charge plus q. Now we want to move the charge in the direction opposite to the direction of the electric field intensity, right? This charge, it is a positive charge q, and I want to move it in that direction. Now let us see that first there must be, as I move the charge from infinity towards the test, that when I enter into the field of the charge plus q, then it will experience a repelling force. So work must be done to move the charge against the electric field, and that work done must be stored in the charge as its electrostatic potential energy. Now, as we know that for the work done, that how much work done actually it requires, as we know that to calculate the work done, is we know that this work done while moving the charge will be equal to what? The work done while moving the charge will be equal to, that will be equal to, this work done will be equal to F dot delta R, right? That is the very simple formula for the work done. Since this is what, this is the A's, this F is the electrostatic force, and you know this electrostatic force on the charged particle is equal to, sorry, q into what, it is q into E into the electric field intensity at that point, right? One is this equation, and you know that, look, as this electric field intensity, it is equal to what, it is equal to k, yeah, that is equal to 1 over 4 pi, well, it is simply, I should write k into q by r square, right? And this delta r, delta r is in fact what? Now look where I want to move the charge. I want to move the charge from infinity. Let I enter into the field. The charge I want to move from the point A towards the point B, right? So as you see, look, the charge particle at the point A, the distance is RA, and at the point B, this distance of the charge from the source charge is RB. So you have the electric field intensity at the point A is EA, and you might have the electric field intensity at the point B is EB. So this, the distance between these two charge particles, this distance where the charge is moved from A to B, that is a delta R in fact. And what I can write this, and what I can write that this is in fact, oh my God, this is in fact equal to what? RA minus what? Minus RB. We have won this. Now look, another important point which I want to tell you, that first note that, that is the sense what, since the distance varies is 1 over r square, so that is, so the force, the electrostatic force is not constant. It is what? It is not constant. It is what? Varying. Therefore, therefore, the work done is what? The work done is variable. Why? Because a variable force acts. The force at the point A is not the same as the force at the point B. So we have won this problem. So in order to calculate the total work done, how we will tackle this problem? We will divide the entire distance between the point 1, between the point A and the point B into n length elements delta r. This is delta r, 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 right? So we will calculate the work done first. Since r1 is very close to point A, so we will calculate the work done between this point first, then between the point r1 and r2, then r2 and r3. Why? Because they are very close to each other and the variation is very small and the work will be nearly constant, and then later on we will add them together, right? So that will be one of the solution towards our problem for what variable work done. So we will calculate the work done between any two consecutive points, right, which are separated by small or infinitesimal distance, right? So that is delta r. The second, since we are moving the charge against the electric field, so the work done will be what? That work done will be negative. Why? Because you know that the electric field is in this direction and the charges move in the opposite direction. So from equation number, this is equation 1, right? So let's, from equation 1 and 2, what I can write that this work done W is equal to minus F into what? Minus F into delta R. Why? Because why a negative sign? The negative sign indicates what? Indicates that the charge is moved against the field. The charge is moved against field. Against the field, and work done must be negative. So you must remember this one. The second important point here, this must be equal minus and F into, what is this? This is RA minus RB. Or we can write that F into what? RB minus RA, or we can write this delta work done. This delta work done could be written as what? It could be written as Q naught into E, Q into E into RB minus RA, like that. We will write it in this way. If you see, it could be like that, but since we have divided it into what? Into very small and infinitesimal distance, so let us see what will be the electric field intensity first. So the electric field intensity, it will be what? Is 1k q by r square. So this r square, 1 over r square, is in fact 1 over ra into 1 over rb, right? It will be 1 over Ra into what? Into 1 over Rb. Why? Because if you remember the gravitational potential energy equation in chapter number, I think 6, when you were in class first year. So we have already derived this and no need to do it. But even if you want to do it, how you can do this thing? Because you know, if you want to find the average, what you will do? Ra by Rb divided by 2. And since you can find the value of the RB from delta R is equal to RB minus RA, you put it here, take the square, simplify, and you will get the same answer. Okay, so let us bring this again there. See here, look. Okay, so we now want to explain it further here, as I already did it there. Now what actually we want to do is to calculate, what is to calculate now the work done between the point A and the point B, like that, as you see. So now look, we will apply this to calculate the work done at what? At the work done at the various points. Okay, so let us do it. That 1 over, that is for now work done between the point A and B. Oh, first we want to do this work done between these 2 points. So look, the variable work done. So the work done will be now applying the above general formula or expression, we can write that the work done, I'm sorry, the work done from point what the work done from the the work done from that is from A to the work done from A to 1, right? How much is this work done? This work done will be equal to what? This work done will be here the hours, but this distance will be equal to what? It will be equal to it will be equal to uh, the force. That force is how much? That is the force is equal to kq into the electric field intensity. So this will be equal to q kq into this q into what? Into it will be equal to what? It will be divided by ra into what? Divided by ra into R1, and as we have already calculated, this delta R is what? Into delta R. This delta R is what? Into delta R. So delta R, which is this thing. So this equals RB minus RA, like this. So you see that the work done from A to 1 point will equals K Q into RB RA by, oh my god, I'm so sorry class, sorry. Why? Because I just want to move it from where? From which point? From this point, from RA to R1. So what I'll be writing this? I'll be writing it is RA minus R1. Sorry, I'm so sorry for RA minus what? R1. So this work done from A to B will be equals K, oh, sorry, from A to 1. It will be equal to K Q Q into RA into RA R1 minus R1 into RA. And what happens? This get cancelled, this get cancelled, and this work done will be K Q into 1 over R1 minus 1 over RA, right? So it will be like this. Similarly, the work done from 1 to 2 point, it will be K Q, and this work done will be equal to what? It will be equal to 1 over R2. It will be equal to what? 1 over R2 minus 1 over R1. It will be equal to like this. Similarly, the work done from 2 to 3 will be equal to KQ into 1 over R3 minus 1 over R2 until that the work done we arrive the work done from like the point, that is from the point N to the point B, right? So this work done will be equal to KQ, and it will be equal to, this work done will be equal to 1 over RB minus 1 over Rn, like that. So if I just add the total work done from A to B, it will be equal to the work done from the A to 1 plus the work done from 2 to 1 to 2 plus 2 to 3 until we arrive the work done from N to B. All these work done. So this work done from A to B will be equal to, you see we have the work done from like that K Q into 1 over R1 minus 1 over RA plus 1 over R2 minus 1 over R1 plus 1 over R3 minus 1 over R2 until we arrive 1 over RB minus 1 over Rn, right? So definitely here we will be having 1 point plus 1 over Rn somewhere here, right? But I cannot write all 1 over Rn point. So you see all these point here, this one will get cancelled with this with that, the 2 with this, the 1 with 1 over R1, this will get cancelled, and this will get cancelled, and this will get cancelled. And at the end, we have left with what? The work done from A to B will be equals KQ into what? It will be equal to KQ into 1, that is minus 1 over RA plus 1 over RB. Or we can write that the work done from A to B, it will be KQ into 1 over RB minus 1 over RA. Now look, A dividing both side by Q. Why? Because we want to know the work done per unit charge. Q. With how much will be this work done per unit charge into Q into 1 over RB minus 1 over R. Now you know that this will get cancelled like that, and we have left that this thing is equal to what? Electric potential. As you know, delta U, electric potential between the point A and the point B, which is equal to KQ into 1 over RB minus 1 over RA. Or this electric potential is equal to VB minus VA. VB minus VA into that is 1 over RA, 1 over RB minus 1 over RA. Right now, look, into KQ. Is, that is point A is where? Is point A is at infinity, right? It is infinity means outside the field, outside field, right? So what does this mean? We have chosen it as a, yeah, if the point A is at infinity, then what will happen? It will be at infinite distance, R will be infinity. So 1 over RA, it will be 0. And at that point, what? At that point, the potential will be what? The potential will be the V, the potential VA will be definitely equal to 0. So what does this means? This means that VB minus 0 is equal to, VB minus 0 is equal to what? It will be equal to KQ into 1 over RB minus 0. R, this VB will be equal to KQ by RB. Generalizing for any R, let's say we say RB is any point inside the electric field R. So what we can then write, that electric potential at any point will be equal to KQ by R. So this is the equation for the electric potential due to a point charge, which is the relation for what? Which is the relation for the electric potential. The electric potential due to a point charge. Due to what? Due to a point charge. For the negative charge, you just put one minus. So that is what? That what is the result? The result is that the this tells that V is directly proportional to the charge and V is inversely proportional to R. Unlike, it has one thing common with the electric field intensity. Electric field intensity is also directly proportional to Q, but that is inversely proportional to 1 over R square. There is 1 over R square, inverse square. Like here it is the inverse proportionality, very simple inverse, V 1 over R. Right? So that is the end of our today lecture. Hope you will learn. Thank you very much for attending the class.